students, welcome to part 4 of the integration review series. In this clip, we're going to be going over the rules for definite integrals, okay? So before we start taking a look at the examples, let's go over the rules for definite integrals real quick, and then we're going to apply those to the examples that we're looking at, okay? So let's write this down. We're going to call this the rules for definite integrals. Well, before I talk about the rules, let me just go over the representations that I'm going to be using to help you understand the reasoning behind the rules. Okay, so your typical definite integral, let's say your integral from a to b of f of x dx. I'm going to be using two models to help you understand this. First is the area model. What does this expression mean within the context of an area? This definite integral is the area under a curve. We're assuming that f is continuous uh, under a certain interval, let's say from a to b. So this integral right here represents the area under the curve, okay? So from here to here. And let's say this function I just drew, this is f of x, okay? So this area under the curve right here, between the curve and the x-axis, is the integral from a to b of f of x dx, okay? Alright, so we can look at it within the context of an area, and if you think about the dimension, what's the dimension of area? The dimension of area is L squared, right? Because you have a length times a length, okay? So this is the area representation. Another way you can think of this, you might have already gone over this in upcoming chapters, is the fundamental theorem of calculus part 2. Basically, this states that this integral from a to b of f of x dx is the antiderivative of the function evaluated at b minus the antiderivative of the function evaluated at a. Okay? So these are the two representations that I'm going to be using to help you understand the reasoning behind some of the rules that we're going to be looking at. Okay? Alright, so with that in mind, let's take a look at the rules for definite integrals. Then we're going to apply them to a problem. Okay? So rules for definite integrals. Alright, so the first one we're going to look at is the order of integration rule. Okay? So number one is order of integration. Order of integration. Alright, so what does this rule say? Basically, it tells you that if you have integral from a to b of f of x dx, and you reverse the order, if you reverse the order of integration, so this goes from a to b, if you go from b to a, in order for these two to be the same, you have to introduce a minus. Okay? So if you switch the order of integration, this becomes a minus. Alright? So just to explain a reason behind this, just to help you understand this, think about the FTC Part II. What does this expression look like? This expression is basically the antiderivative f of evaluated at b minus the antiderivative of f evaluated at a. All right. What happens when I switch these two around? When I switch these two around, I'm going to have negative antiderivative at a plus antiderivative at b. Right. When I factor out the minus, I'll have parentheses antiderivative evaluated at a minus the antiderivative evaluated at b. Okay. So what on earth does this mean? This is basically uh, the negative of the antiderivative of f of x, the integral of f of x evaluated from the first point of evaluation goes on the top, there's the upper limit over, and then that's the lower limit dx. Okay, so we can see that we just switched the antiderivatives. That's what introduced this minus right here. So anytime you switch the order of integration, you have to introduce a minus right here. Okay, so that's why that's the case. All right, now let's take a look at the second rule. Second rule is known as the zero rule. Okay, zero rule, and that basically says that if your limits of integration are the same. So let's say you're going from b to b of g of x dx. This is going to be equal to 0. Okay? So why is this the case? Well, this is because you're enclosing a zero area. Okay? Zero area. So let's say you had a function. This is just a side example. You don't have to write this down. Let's say you had a function of this nature. Uh, and then you're looking for the area under the curve bounded by just a line. It's like this. Okay? So we know that this function has a height, right? It has a height. But the question is, um, what is the width of this function, right? What's the width of this function? The width of this function is 0. It has 0 width, right? So since it has 0 width, it has 0 area, okay? So basically, the area under this curve is basically 0 because you have 0 area, okay? All right, and then because the limit is b, you're going from b to b, you have to have a area to enclose in order to have an output as an area. All right. So this is why the antiderivative, when the limits are the same, is 0 because you're enclosing 0 area. Okay. Now that's using the area model. If you wanted to use the FTC Part 2, it's way more obvious. If I were using the FTC Part 2, this would basically be the antiderivative evaluated at b minus the antiderivative evaluated at b. You're subtracting the same thing and you're going to get 0. Alright? So that's why we have the 0 property of intervals. Okay, the next property is the constant multiple. So, this is number 3. The constant multiple. So what is that? The constant multiple is just scaling an area. Okay? We have to be careful with our dimensions here because it helps us avoid making mistakes. So if I have the antiderivative from a to b of, let's say, a function g of x uh, multiplied by a constant, so k times g of x dx. The constant multiple rule basically says that this is equal to k times the antiderivative from a to b of g of x dx. So basically, you can always factor out the multiple or out of your the value, the expression that you're integrating. Okay. All right. So let's take a look at. I'm going to use FTC Part 2 to basically help you understand what this how this expression comes about. So let's say we didn't know the constant multiple rule and we failed to factor out k from the integrand before we evaluated the definite integral. What we'll have is we'll have k multiplied by the antiderivative at b. Let me change the color because we're not supposed to write in this. This is just a side note. I'm just showing you why. So we're going to have k multiplied by the antiderivative of g evaluated at b minus k times the antiderivative of g evaluated at a. You notice what I can do here? K and k are factors of, are multiples of these two antiderivatives evaluated at these two points, so I can always factor out the k, right? So we have k times the antiderivative of g evaluated at b minus the antiderivative of g evaluated at a, right? And then what is this inner piece right here? That's the antiderivative, right? So we have k times the antiderivative of g of x, evaluating from a to b, of g of x dx. Okay, so that basically shows you that you're scaling. And if you think about the area model, you're just scaling the area by a factor of k. Okay, so this is much more obvious to see the connection between these two formulas. All right, so keep that in mind. You can always factor a constant out of a definite integral, if possible. The next rule is the sum of difference rule. Okay, sum and difference. Now, the sum of difference rule is basically just tells you that you can add or subtract integrals. Okay, so if you have an antiderivative from a to b of two functions, let's say f of x plus or minus g of x dx, this sum can be distributed to the individual functions, okay? So this can be written as, this is equal to the antiderivative from a to b of f of x dx plus or minus the antiderivative from a to b of g of x dx. Okay, so there you have it. All right, and if you think about this, using the area model, this basically indicates addition or subtraction of the height of your function. If you're adding, it's going to be higher, and if you're subtracting, it's going to be lower. Okay, but to help you understand, let me use the FTC Part II to help you see why this makes sense. So, think about FTC Part II. This antiderivative that we have right here from a to b of f of x plus or minus g of x dx. You can do this one at a time, but I'm going to do them simultaneously, okay? Basically is the antiderivative evaluated at b plus or minus the antiderivative of g evaluated at b, this whole expression minus the antiderivative of f evaluated at a plus or minus the antiderivative of g evaluated at a. Okay, so you notice we can rewrite this as, because of the commutative property, we can just drop it. Let's just write it like this: f antiderivative of f evaluated at b plus or minus antiderivative of g evaluated at b minus antiderivative of f of a. This becomes, if you distribute that to that, it becomes minus or plus. Minus or plus is the same thing as plus or minus g of a. Okay. All right. You remember addition? We can just rewrite the expressions. Just move the expressions with your sign. So we have f of b minus f of a plus or minus g of b plus or minus g of a. Okay. All right, and then we can just combine these two in the following setting. We can write this as the antiderivative of b minus the antiderivative of a, and then plus or minus the antiderivative of b for the g component minus the antiderivative of a. Okay, and then this is basically the antiderivative from a to b of f of x dx plus or minus the antiderivative from a to b of g of x dx. Okay, so there you see it. So just remember, when you're adding or subtracting, you can always distribute this integral into both of them. All right. All right. Now let's take a look at the last rule that we're going to be using for the examples, which is known as the additive rule. Okay. So the additive rule, number 5, additive, basically says that if you're integrating from a to b of f of x dx plus v to c of f of x dx, uh, that is can be simply written as the integral from a all the way to c of f of x dx. Okay, so if you think about it, let's use the area model that will help us understand this one. So what is it that we're doing here? We're just basically adding two areas that are next to each other. Okay, so let's say we have this function, and then this is a, and then this is b, and then this is c. Okay, all right, so what is this telling us? This first integral right here is the first area, right? Area 1 right here. Let's say this is a1. This integral right here is a1. It's a different color. This integral right here is a1, and this is area 1 right here, the integral from a to b, right? And then this second integral is a sub 2, right? So since we continue from where we stopped, this region right here is a sub 2. But I notice that the entire region from the integral from a to b, c is basically a1 plus a2. So instead of writing them like a to b and b to c, we can write them as one combined integral, which is what's expressed by this notation right here. So this expression, a to c, basically means you're adding both areas. You notice that it's contiguous, right? There isn't any breaks whatsoever. So you can write them as one combined integral. So that sums the entire region bounded by these two areas that are adjacent to each other. Okay, so that's the reasoning behind this additive property. Okay, so now that we have our properties down, we're going to use them to solve some examples. Okay. All right. So let's take a look at the following example. All right. So it says, suppose that h and g are continuous functions, and that the antiderivative from 1 to 6 of h of x is negative over 5. Antiderivative from 2 to 1 of h of x is 12 over 5, and then antiderivative from 1 to 3 of g of x is 5, and then the antiderivative of g of x from 6 to 3 is 3 root 2. We're going to find the value of each one of these, okay? So let's go ahead and get started. We're going to take a look at the first one, which is A. A says we're going to find um, square root of 21 times the antiderivative from 6 to 1 of h of x dx. Alright, so how do we find this? Well, we know the antiderivative from 1 to 6 is negative 3 over 5, right? So what we're going to do is we're going to use the order of integration rule to switch the order here. Remember, when you switch the order, you switch the sign, right? So this becomes the square root of 21 times negative antiderivative from 1 to 6 of h of x dx. Okay, notice I switch the order and then I introduce this minus. Okay, so now we can now replace this piece with negative 3 over 5. Okay, so I'm going to substitute this entire antiderivative with negative 3 over 5. So this becomes root 21 times negative 3 over 5. All right. And when you multiply that, you have root 21 minus times minus is plus times 3 over 5. And your final answer is 3 root 21 over 5. Okay? So that's the answer to letter A. Alright, let's move on to option B. We're asked to find the definite integral of g of x from 6 to 1. So let's write that down. So for B, what is the definite integral from 6 to 1 of g of x dx? Alright, so I know the integral from 1 to 3 and then from 6 to 3. So I need to find the antiderivative from 6 to 1. Okay. Alright, so let's see what we can do here. So from 6 to 1, I can write this as the antiderivative from 1 to 6 of g of x dx. Okay, what did I just do? I just switched the order of integration. So using the order rule of definite integrals, when you switch the order, you have to introduce a minus. Okay. All right. Now let's see. Can I split this apart? And the 3 is between 1 and 6, so I can write this as negative the opposite of parentheses, as be careful with the sign here, the antiderivative from 1, sorry about that, antiderivative from 1 to 3 of g of x dx plus the antiderivative from 3 to 6 of g of x dx. Okay, now what rule did I just use? I just used the additive rule. Okay, I can break it apart. I chose 3 because I know, based on what I'm given, that 3 is a midpoint between 1 and 6, and I know that it's associated with g. Alright? So I know the value of this from 1 to 3 of g of x dx is 5, but I have a problem here. I know the value from 6 to 3. I don't know the value from 3 to 6. So I'm going to use the order of integration rule again. This is going to be minus times the antiderivative from 1 to 3, which I know, minus negating or switching the sign gives me the right to switch the order of integration from 6 to 3 of g of x dx. Okay? Alright, now I can substitute with ease. So I know that the first definite integral, I left out my g of dx, sorry. Anyway, I know that my first definite integral is 5, so put a 5 here. 5 minus, and then my second definite integral is 3 over 2, so minus 3 over 2. And then we'll distribute this minus that we had out here because of the initial switch, so it's going to become negative 5 plus 3 root 2. Okay, so that's the answer to option B. Alright, let's go ahead and consider option letter C. What is it that we're looking for in that case? Let's look at it. For option letter C, we're looking for the antiderivative from 1 to 6 of g of x minus h of x. Okay? So, alright, so let's write it down. So C, we're looking for the definite integral from 1 to 6 of g of x minus h of x dx. Okay? Alright, so obviously we're going to be using the difference rule here. So this can be written as the antiderivative of 1 to 6 of g of x dx minus the antiderivative from 1 to 6 of h of x dx. Okay? Alright, so I know that the antiderivative of h of x is negative 3 root 5, but how about 1 to 6 of g of x? Well, we just did it, right? What we just did is we did 6 to 1 in option B, okay? So in order to use that, I need to switch this order right here. This I'll write as the antiderivative of 6 to 1 of g of x dx so that I can use my answer from part B, okay? From 1 to 6 of h of x dx. Now, what did I do with the first integral? I switched the order, so I have to introduce a minus using the order of integration rule, okay? So, remember our answer from option B, you can look at your notes, is we got negative 5 plus 3 over 2. Put that in there. Minus, and this one is obvious, it's given to us, 1 to 6 of h of x is negative 3 over 5, so parentheses negative 3 over 5. So simplify further, we'll have distribute this minus to these two. 5 minus 3 root 2, and then plus 3 over 5. Put this as a fraction. Find the LCD so I can combine these two together times by 5 top and bottom. So this basically becomes 25 plus 3 is 28. So this becomes 28 over 5 minus 3 root 2. Alright, so there goes your final answer. Alright, let's move on to letter D. We are looking for, oh boy, I think I jumped from C to E. Let's look at E then. Let's call it D. So for D, which is E in this case, we're looking for the antiderivative from 2 to 6 of negative 3h of x dx. Okay? First thing we have to do is we have to use a constant multiple rule, which gives us the ability to factor out this constant from the integrand. So this is going to be negative 3 times the antiderivative from 2 to 6 of h of x dx. Okay? So now what is the antiderivative from 2 to 6? Well, I know the antiderivative from 1 to 6 and 1 to 2. So how do I figure out 1 to 6? To help you understand what I'm going to do here, let me just use a line to illustrate this. So I know 1 to 6, and I also know 1 to 2. Okay, so I know this entire integral, and I know this integral. Okay, so how do I find this piece? How do I find this remaining piece right here from 2 to 6? Well, I could use the sum and difference rule to subtract the entire length, which is 1 to 6. So I'll do 1 to 6, and I'm going to subtract uh, 1 to 2 from 1 to 6, and that will give me the antiderivative from 2 to 6. Okay, so subtract this little piece, 1 to 2, this piece right here, from the entire length, and that will give me this residual length right here, which is 2 to 6, which is what I want. Okay, so that's what I'm going to do. That's the plan of action. Subtract this little piece from the entire thing. Okay, so let's set it up. I'm going to go, let's leave this negative 3 out here, times the antiderivative of the entire area, which is from 1 to 6, of h of x dx, minus the piece I know, other piece I know, which is from 1 to 2, this little piece right here. That will give me, let's see, from 1 to 2. You see, that will give me the antiderivative from 6 to 2. Okay? Alright, so there you have it, okay? So what we're using here is basically a derivative of the additive rule. If this doesn't make sense, let me just show you another rendition to help you understand. Check this out. If I'm going from 1 to 6 of a function, f of x dx, if I define that as an antiderivative using the additive property of from 1 to 2 of f of x dx plus the antiderivative from 2 to 6 of f of x dx. If I wanted to find this antiderivative, just this piece right here, what do? I'll subtract this integral from both sides, right? So what I'll do is, to get what this value is, which is what I wanted, I'll just subtract this from both sides, right? So I just subtract this one, the antiderivative 1 to 2 of f of x dx from both sides. And then what I'm going to end up with is, when you use the reflexive property of equality, I'm going to have the antiderivative from 2 to 6 of f of x dx, which is basically the entire area, antiderivative from 1 to 6 of f of x dx, minus the other piece right here, the antiderivative from 1 to 2 of f of x dx. So this is just a different manipulation or transformation of the original additive rule that we came up with, okay? So since you have this, since you can express this entire sum as a sum of two pieces, you can find any piece by subtracting the other piece from the entire sum, okay? So there, that's what we're doing right here. This is a whole, and this is one of the pieces to get the other piece. All right, so now that we have it set up, let's go ahead and finish it off. Let's hope we have these two. No, we don't. We have only one. So we have to do another switch because this goes from 2 to 1. So let's do one more switch, and then we can go ahead and finish this up, okay? So this is going to become negative 3 times the antiderivative from 1 to 6 of h of x dx. If I switch the order of this integration so it matches with what I have up here, 2 to 1 of h of x dx, then I have to introduce a minus, but there's a minus here already, so minus times a minus is a plus. Alright, now we're good to substitute. So the first one is negative 3 over 5, so we have negative 3 times negative 3 over 5, plus the second one is 12 over 5, plus 12 over 5, okay? Alright, let's evaluate what's in the parentheses first using order of operation. So we have negative 3 times. Negative 3 plus 12 is 9 over 5. And we'll multiply that, you have negative 27 over 5. Alright, so there goes the answer to option letter E and B. Okay? Alright, now let's go ahead and consider the last one. Last but not the least is the easiest one out of all of them. Option E. Where is that? Option E. I called it F here, so let's call that E. So for option E, we're evaluating the integral from negative from root 5 to root 5 of f of x dx. Okay, that reminds me, just one quick point to note is that there isn't any product or quotient rule for integrals, okay? So you have to be really careful, okay? So, careful. Let me put this in red. Careful. Uh, so, these following rules do not exist. So, do not exist. So, now some people might say, oh, wait a minute. Integral from a to b of f of x times g of x dx, this right here, is equal to the integral from a to b of f of x dx times the integral from a to b of g of x dx. This is false. Okay, false, false, false. Please do not do this. Okay, these dimensions are inconsistent if you think about it. Now this, like I told you before, is an area. So what's the dimension of an area? Is L squared, right? How about this right here? This is the product of two areas. So we have L squared times L squared, which is L to the fourth. So this is 4 dimension. This is 2 dimension. You can see that the dimensions are inconsistent. That's just a way to show you that this is false. So do not distribute the integral over a product. Okay, this is wrong. Don't do this. And also, don't do distribute the integral over a quotient either. So some people might say, oh, wait a minute. The integral from a to b of f of x over g of x dx is equal to the integral from a to b of f of x dx divided by the integral from a to b of g of x dx. This is also false. Do not do this, okay? If you think about the dimensions, they're also inconsistent here. If you look at this, this is an area, right? This entire integral is an area, L squared. But this one right here is an area divided by an area, okay? Which has no dimensions, is basically L to the 0. You see that there's a dimensional inconsistency here. So this is terribly wrong. So do not try to do this, all right? Because they're inaccurate. You can only distribute the integral over sum and differences, right? Remember, you can only do this is the only thing that's true. You can do this from a to b of f of x plus g of x. See, we have something like this, a sum. Like we talked about before, you can distribute it over the sum like this from a to b of f of x dx plus integral from a to b of g of x dx. Okay? If it's a sum, that's perfectly fine. If it's the difference, that's perfectly fine also. I did both of them simultaneously before, just to show you. But just remember, you can distribute the integral over sum and differences. You can do term by term integration if the terms are separated by pluses and minuses. Okay? But if it's product or quotient, you cannot distribute the integral into both of them. Okay? So this is fine and this is fine. But if you have plus or minus, no, you cannot do it. Okay? So keep that in mind. Alright. So let's take a look at the problem we have. Even though we're not going to be making use of these rules I just mentioned, but it's just good to keep these facts in mind because there might be some common mistakes that people make. So let's take a look at the example. So we're going from root 5 to root 5 of g of x of f of x over g of x to the third dx. So how do we evaluate this? Well, guess what? We can use the zero rule. Whenever the limits of integration are the same, it's as though we are computing a zero area, right? So what's the area of zero area? This is simply 0 using the zero rule because these two limits are exactly the same. So the answer is 0. Okay? So there you have it. But thanks so much for taking the time to watch this video. You can feel free to subscribe to my channel by clicking up here. More videos can be found on mathreserve.com. Thanks again and have a wonderful day.